For the course project of Energy Management and Environment, Group 10 will be presenting the energy assessment of AN-NUR MOSQUE of University Technology Petronas. Our team members consist of 5 students from the backgrounds of mechanical engineering and electrical and electronics engineering.
AN-NUR Mosque is both a spiritual and community hub for UTP, designed to integrate traditional Islamic architecture with modern sustainability features. Its focus on natural lighting, ventilation, and energy efficiency showcases a growing global emphasis on sustainability in religious buildings. Despite its sustainable design, the mosque faced key challenges, including high energy consumption due to artificial lighting and HVAC systems, thermal comfort issues with temperature and humidity regulation needing improvement, and lastly, building materials and envelope, such as walls, roofs, and windows, require better insulation to enhance energy efficiency. To address these challenges, our study aims to analyze energy consumption and identify areas for improvement, assess the effectiveness of orientation, envelope, and ventilation systems, benchmark energy performance against sustainability standards, recommend cost-effective solutions like efficient lighting, and lastly, evaluate the feasibility and payback period of these improvements.
So our project focused on enhancing energy efficiency through three key areas. The first one being building orientation audits, where we evaluate sun direction and heat movement to optimize window placement, insulation, and roofing. The second point is to the building envelope audit, where we assess walls, floors, doors, and also windows to identify insulation needs and minimize heat gain. The third one is being the energy audit, where we measure lighting levels, temperature, humidity, and wind speed. Where we focus also improving lighting and HVAC systems. Ultimately, our goal is to identify energy-saving strategies that help reduce cost and environmental impact while supporting UTP's sustainability goals. So as shown in the slide, the detailed design and estimation of the dimension of a structural block are presented using metric units. The drawing highlights the architectural layout, focusing on the floor plan, including key structural features and spatial locations. The major dimension for the main prayer hall, such as the total width, is 30,000 millimeter, and length is also 30,000 millimeter, are provided along with detailed sectional measurements.
A building audit was conducted to assess the mosque's energy performance and efficiency. We focus on three areas. Orientation audit examines natural lighting and ventilation based on positioning. Envelope audit evaluates insulation and heat loss or gain in walls, roofs, and windows. And lastly, energy audit measures energy usage in lighting, HVAC, and appliances to identify inefficiencies. For the building orientation audit, firstly, geographical. The mosque is aligned to the Qibla direction, but is also positioned to maximize natural lighting and ventilation. Its location in an open landscape allows for unobstructed daylight penetration, enhancing energy efficiency. Next, several architectural features influence thermal performance and lighting efficiency, such as the main prayer hall, with tempered glass windows, reduces artificial lighting but contributes to heat gain. The dome structure, which diffuses light naturally but requires ventilation to prevent heat buildup. The stairs and mezzanine areas, designed with openings for vertical daylight penetration, reduce reliance on artificial lighting. Shading considerations, like overhangs, provide some relief but could be enhanced with louvers or trees. And finally, solar path analysis reveals that heat control strategies like selective glass coatings or shading screens are essential in Malaysia's tropical climate. Furthermore, the mosque employs passive cooling techniques like the stack effect, where warm air exits via upper-level fans and large openings that enhance cross-ventilation. The elevated design reduces ground heat retention, but further alignment of openings with prevailing wind directions, along with adjustable fans and perforated facade panels, could improve airflow control.
Moving on to building envelope audit. By definition, building envelope audit consists of evaluation of exterior elements of the building that separates the interior from the exterior environment of the building. Why is this audit important? It is to assess the performance of the building envelope in terms of energy efficiency, thermal insulation, moisture control, and overall durability. Building envelope audits consist of two key components, which are building characteristics and construction, and windows and doors characteristics. From our detailed site visit of the AN-NUR Mosque of UTP, we have gathered the following information. We have gathered that the overall building and land area is about 4,000 square meters, the main prayer hall area is about 600 square meters, and the material of the building floor is made up of marble and ceramic tiles, as well as the material for the building wall is reinforced concrete. Now, moving on to the windows and doors characteristics. To briefly explain, let's begin with the window. The windows are with the height and width of 1.56 meters times 1.14 meters. And the windows are operable windows. The glass walls on the upper half of the prayer hall are assumed to be affixed windows. The windows are unglazed, and there are no visible cracked or broken panes seen. And for the weather stripping condition, the windows are adequate. Doors, on the other hand, the mosque uses electrical sliding doors with the typical frame type of aluminum. Finally, the percentage of estimated gross wall area of the wall area of the main prayer hall compared to the land area is about 15%. Now let's dissect the tools and methods used for environmental audit. We use infrared thermal sensors to measure temperature of various areas of the building. We also use an anemometer to measure the wind speed inside and outside of the building. Next, a light meter is used to measure the different light levels of various spaces of the building. And finally, we use a humidity sensor to measure humidity levels at different areas of the building. From the environmental audit we've conducted, these are the data that we've recorded. For temperature, the average temperature for the center of the prayer hall is 22.75 degrees Celsius, whereas for the location of nearing the window, it is about 22.78 degrees Celsius. Whereas for humidity and relative humidity, the center of the prayer hall has the average of 71.40, whereas the one near the window has an average of 71.53% of relative humidity. The followings are the breakdown of calculations for humidity. Assuming we have a baseline of wet bulb temperature of 18 degrees Celsius, the difference in temperature equals to wet bulb temperature minus the baseline, which is 19.92 degrees Celsius that we've assumed, minus 18 degrees Celsius equal to 1.92 degrees Celsius. For a single hour, the wet bulb degree hour, which is WBDH, would be 1.92, whereas for over a whole year, assuming the conditions are constant, WBDH annual equals to 1.92 times 8,760 hours per year, equating to 16,819.2, approximately 17,000. The following are the data recorded for wind speed. Wind speed are measured in meter per second. We've measured wind speed for two different locations, one inside the prayer hall and the other one outside the mosque. The average for inside the prayer hall is about 0.37 meter per second, whereas the average for outside the mosque is slightly higher, being 1.38 meter per second. Based on this table, the average wind speed for outside the mosque is 1.38 meter per second. This is because it is more effective to measure wind speed outside the building. We multiply the average wind speed of 1.38 meter per second with the conversion factor, which equals to 3.08 mph. And finally, for the last part of the environmental audit are the recorded data for light levels. Light levels are measured in lux. We've measured light levels in two different locations. The first location being the center of the prayer hall with an average of 416.5 lux, and the second location is nearing the window, also inside the prayer hall, with the average of 677.3 lux.
Now let me present the energy accounting form of Masjid AN-NUR UTP Prayer Hall located on the first floor. This form gives us a detailed monthly breakdown of the mosque electricity usage, total energy costs, and key performance indices such as the building energy index, load factor, and energy use intensity. From the site assessment, we estimated the daily energy consumption to be around 287.16 kilowatt hours, which leads to an annual consumption of approximately 104,811 0.94 kilowatt hours. These values are based on actual electrical components in use and standardized assumption for their operating hours. The total floor area of the prayer hall is 900 square meters, or about 9,688 square feet, and we applied the standard energy conversion factor of 0.003413 to convert kilowatt hours into MMBTU for energy benchmarking. This accounting forms the foundation for comparing the building performance against national energy efficiency benchmarks and identifying areas where improvement can be made. Now let's dive into the electric demand calculation for Masjid AN-NUR UTP Prayer Hall on the first floor. The purpose of this section is to assess the energy usage of various components within the mosque, including the lighting system, security equipment, cooling system, and other electrical appliances. Firstly, we have the lighting system, which includes 38 CFL downlight bulbs rated at 8 watt each, 36 halogen lamp rated at 18 watt, and 15 fluorescent lamps rated at 28 watt. These lighting components are essential in providing ambient light for the mosque. Next, for security and surveillance, the mosque use 5 IP CCTV cameras, each consuming 15 watt, and 9 automatic sliding doors, each rated at 200 watt to manage entry. For audiovisual equipment, there are 2 televisions rated at 320 watt each, 21 3-pin socket outlet assumed to consume about 150 watt each, and 2 speakers rated at 100 watts each for sound applications. In terms of cooling, the prayer hall is equipped with 1 portable air conditioner rated at 1000 watt. Finally, the air handling units, AHU, which maintain the thermal comfort inside the hall, consists of 75 vents, each rated at 129.47 watt. We calculated the total daily energy consumption for each component by multiplying its power rating, the number of hours used daily, and the quantity of each unit. As shown in the table, the air handling units contribute the most significant energy consumption, which is 155.388 kilowatt hour per day, followed by the automatic sliding door and fluorescent lamps. This calculation help us understand the most energy consumption patterns, which is key to identifying area where energy saving measures can be implemented. Let's now look at the Building Energy Index and energy intensity to understand how efficient energy is being used in the Masjid AN-NUR UTP Prayer Hall. The Building Energy Index is a metric that evaluates the overall energy performance of a building. It reflects how much energy is consumed per square meter of floor area annually. This allows us to compare energy efficiency across different buildings. In our case, the most calculated BEI is 117.45, which is slightly above the recommended benchmark of 110 for non-residential buildings. This suggests that the building energy consumption is higher than ideal. Therefore, there is a need for energy-saving initiatives or for potential retrofitting of system to optimize energy use and bring the building closer to its ideal energy performance. While BEI focuses on energy use relative to floor area, we also need to understand energy intensity, which assess the energy consumption based on the number of occupants. This matrix is crucial in high occupancy buildings such as mosques. There is usage patterns can vary. By calculating the energy intensity, we can see how efficiently energy is being used per person on a daily basis. For Masjid AN-NUR UTP, with an estimated 850 occupants, the energy intensity is 0.341, which is quite efficient. This low energy intensity shows that despite the slightly high BEI, the mosque is performing well in terms of energy use per person. This reinforces the idea that even with large occupancy, energy management strategies can be effective in reducing waste and ensuring a comfortable environment. Let's now discuss suggested improvements for Masjid AN-NUR UTP and how they can lead to significant energy savings. One of the most impactful energy saving measures is the addition of curtains to the window facing the outside area. These windows are exposed to direct sunlight, which leads to increased heat inside the mosque. By installing thermal or heat reflective curtains, we can reduce the amount of heat entering the building. This will lower the demand on the air handling units, which are responsible for cooling the buildings. With less heat entering, the cooling system will be more efficient, resulting in energy savings and a more comfortable environment. Another efficient solution is applying tinted film to the 48 windows in the prayer hall. The windows are approximately 1.14 meters wide by 1.56 meters tall. Solar control tinting can reduce the amount of heat transmitted through the glass, which means the cooling system will need to work less. Not only does this improve energy efficiency, but the tinting also enhance occupant comfort by reducing glare and maintaining privacy. Another major improvement is to replace the current light bulbs with LED bulbs. LED bulbs consume 75% less energy than incandescent bulbs and have a longer lifespan. They are also more efficient and generate less heat, which help reduce the cooling load. This change will lower both electricity bills and the mosque carbon footprint, contributing to sustainability. When we combine this improvement, curtains, tinted windows, and LED tinting, LED lighting, the most overall energy consumption will decrease significantly. This improvement not only reduce energy use but also enhance the comfort of the occupants while reducing the environmental impact. Ultimately, this measure will lead to long-term energy savings and support the most sustainability goals.
An economic analysis was conducted to compare energy costs before and after retrofitting, with a total investment of 26,470 ringgit. Key upgrades includes motorized curtains in 6 units to reduce heat gain, costing 12,000 ringgit, and 3M efficient 30 tinted film on 48 windows to block 70% of solar heat, costing 13,200 ringgit. And lastly, CFL bulbs were replaced with LED bulbs for 570 ringgit to reduce the power consumption. Annual maintenance costs of 700 ringgit were factored in to ensure sustained efficiency. These upgrades provide long-term energy savings and lower the operational costs, making the investment highly beneficial. Now, we will proceed with the annual energy savings calculation after the retrofitting measures. One of the major upgrades is the replacement of CFL bulbs with LED bulbs. Previously, CFL bulbs consumed 12 watt per unit, while the new LED bulbs use only 8 watt per unit. This transition has reduced the total daily power consumption for lighting from 7,296 watt to 4,864 watt. Despite the lower energy usage, LED bulbs provide the same level of illumination, ensuring efficiency without compromising the brightness. Another key improvement is the installation of tinted film and motorized curtains. The 3M efficient 30 window film blocks up to 70% of total solar energy, while the motorized curtain help control sunlight exposure. These measures significantly reduce heat gain, helping to maintain a stable indoor temperature and lowering the cooling demand within the facility. In addition, the portable air conditioner and air handling unit now operate with 20% lower energy consumption. The portable air conditioner's power usage has been reduced from 1000 watt per unit to 800 watt per unit, while the AHU's consumption decreased from 129.47 watt per unit to 103.58 watt per unit. These reductions lead to substantial energy savings over time. To assess the impact of the retrofitting measures, we compared the annual energy consumption before and after the upgrades. By calculating the total energy usage and finding the difference, we can determine the actual energy savings achieved. As shown in table below, the daily energy consumption has decreased from 289.61 kilowatt-hour to 252.89 kilowatt-hour, resulting in a savings of 56.72 kilowatt-hour per day, which is a 12.7% reduction. On a monthly basis, the energy consumption has dropped from 8,807.70 kilowatt-hour to 7,733.82 kilowatt-hour, providing savings of 1,073.9 kilowatt-hour per month, or a 12.2% reduction. Annually, the total energy savings amount to 12,886.8 kilowatt-hour, reducing the overall consumption from 105,692.65 kilowatt-hour to 92,805.85 kilowatt-hour, maintaining the same 12.2% reduction rate. These results clearly demonstrate the effectiveness of the retrofitting measures, which have significantly reduced energy usage, leading to lower operational costs and improved efficiency. Now, we will proceed with the feasibility study and payback period. To determine the monthly savings after implementing the retrofitting measures, we calculated the energy consumption before and after the upgrades using the official Tenaga Nasional Berhad (TNB) website. As shown in the figure below, before the retrofitting, the monthly electricity bill was 6,231 ringgit and 67 cents, and after the retrofitting, the bill was reduced to 5,453 ringgit and 43 cents. This results in a monthly cost savings of 778 ringgit and 24 cents. When we project these savings over a year, the annual electricity cost reduction amounts to 9,338 ringgit and 88 cents. To assess the financial viability of the retrofitting measures, we calculate the payback period using the formula. Payback period equal to total cost over annual cash flow. From this formula, we find out that our payback period is 2.83 years. However, considering the time value of money, we use a 10% discount rate to calculate the discounted payback period. Based on the present value of cash flows, the discounted payback period is 3.51 years. The feasibility study confirms that the retrofitting project is financially viable. The investment of 26,470 ringgit results in annual savings of 9,338 ringgit and 88 cents, with a simple payback period of 2.83 years and a discounted payback period of 3.51 years. Since both payback periods are under 5 years, the project is both economically and environmentally sustainable, making it a worthwhile investment.
In conclusion, the sustainability assessment of Masjid AN-NUR at UTP successfully met all of our objectives. We have analyzed energy consumption, identifying inefficiencies and area for improvement. We also have assessed the building orientation, envelope, and ventilation, proposing solutions like improved insulation and natural ventilation. We benchmark the energy performance against sustainability standards, identifying the best practices. We also have recommended the cost-effective upgrades, including the likes of LED lighting, motion sensor, and also smart controls to enhance the efficiency. Finally, we also have evaluated the feasibility and payback period, ensuring financial viability. These findings provide a roadmap for improving energy efficiency and sustainability, making Masjid An-NUR a model for green architecture at UTP. Thank you so much.